So, just kind of put this in perspective. So, you guys remember this slide we covered? I know it's way back early. This slide, we were talking about winds, and I don't want to go way back, but in chapter 6, it's really important. In chapter 6, we talked about wind is created as air goes from a high to a low pressure. And if you're a visual person, I can almost see this. We call this a pressure gradient. Anytime you hear the word gradient, it just means difference in. Gradients are biological, because like if you have like a cell membrane and you have more salt in than out, then basically you can have salt moving out of your cell into the surroundings. It's a gradient. It happens. This just happens to be a pressure gradient, and I don't know if I mentioned before, I think I did, yeah. It's called a pressure gradient, and it's called actually pressure force gradient. And that creates winds. Now, chapter 7, we kind of talk about different winds. We talk about the little winds, the medium-sized winds, and the big winds. And I'm pretty sure we spent a little bit of time talking about these middle-sized winds. Do you remember we talked about the country breeze was the last thing we talked about. Talked about the sea breeze, the valley breeze, the mountain breeze, and you know where it's coming from if you hear the word before breeze. Okay? So now we need to talk about the big winds, the big daddies. Now they're big by two reasons. They're big actually because of their size. They're big because of their size, but they're also big because of how long they last. Okay, so they're big because of two reasons. So I think I've got a friend who got his master's in like the history of science. I just would be amazed to see how the baby steps, some of them weren't quite so baby, that we've taken along the way to get to what we know today. It's just totally amazing. But we know a lot more about air circulation than we did in 1735. But actually, George Hadley, Sir Hadley, started it off. And he said, near the equator, one of the things you guys knew before coming to this class is you should visit the equator. You can count on some nice warm days, right? Okay. One of the things we know about warm air is warm air, just like air in your house, wants to rise. So what Hadley said is basically this warm air is going to rise. Now, in an earlier chapter, we talked about kind of this. There's Mr. Hayes. He's so funny. He likes these classes too. He's funny. He probably likes it. In an earlier life, we talked about the layers of the Earth's atmosphere. We said this is the troposphere, stratosphere, mesosphere, thermosphere. Okay. So what happens though is basically that air rises from near the equator, and we're going to switch it up here in a minute. We're actually going to call that the Intertropical Convergence Zone, ITCZ. But near the equator, it's a hot spot. It rises and hits the tropopause, which is the top of the troposphere. Hits the tropopause, and it goes both ways. That's what Hadley said. Okay, and then as it goes this, it's kind of like what we know about other convections. It cools down, so it sinks. It rides along the Earth's surface. It comes up. Okay, so Hadley actually had two cells. This is Hadley's two-cell model. Oops, sorry. It's on the next book. Next slide. So actually, Hadley was onto something, and when we come up with the way it really works, what we know more is we kind of start with his premise. Okay, but he did not take into account, like the slide says, the rotation. Oops, I apologize. Rotation of the Earth. Counterclockwise. So this is what George Hadley said. You can kind of see the hot spot near the equator. And we've got some figures coming up here that try to kind of throw 3 dimensions into it, so hopefully you can kind of see that. I think they do a pretty good job. The solid sphere is the Earth, okay? And then you kind of see what's happening kind of to the air on top of the Earth. Okay, it's rising, hits the tropopause, goes along the top of the tropopause, comes over here, sinks, and it rides along the Earth's surface like that, okay? We call this a, it's funny, because this is one of my things. I would call this a two-cell model. I would, because there's a cell there and a cell here. Oh, would you quit? I would call it a 2-cell model. But they call it a single-cell model, so we'll just have to go with that. Okay. So it doesn't rotate. Now, this is Hadley's model on steroids. But this is much more what it really does. And they call this the 3-cell model, which I would say it's 6 cells. So you're going to see this figure a few times, so let's just kind of take a look at it. Okay, so you see a cell here, we'll call this 1N because of the northern hemisphere, 2N, there's another cell, 3N, okay? We'll call this 1S for southern hemisphere, you can pick a different color, 1S, 2S, 3S, it's kind of hiding down there. So I got 6, they call the 3-cell model, okay? 3 in kind of each hemisphere. And we're going to break it apart. In fact, I think I'm going to need to close that door. We're going to break it apart, and we're going to, but we're going to see a video on it. Free to cut this out and put it on your pillow to kind of digest the material. But basically, you kind of see our 3 cells here, and we'll be talking more about those. But they kind of start here. I have it at the equator, but I'm going to kind of have to backtrack on that a little bit. It's not always right at the equator. It wanders, just like she talked about, and we'll talk about more. Okay, but basically we have these 3 circulation cells, and they're kind of like, well, we'll talk about each one of them now. All right, so starting with the Hadley cell. I'm sure it's named after George Hadley. But do you see where actually we have a pair of Hadley cells? We have a Hadley cell in the northern hemisphere and a Hadley cell in the southern hemisphere. Okay, so this slide kind of talks you through what's happening. Basically, air comes up, just like Hadley said, hits the tropopause, and it goes both ways. The difference, though, what Hadley says is it will travel to the poles and then complete one cell. But what we know is it kind of bunches up about 30 degrees, just like the slide said. It bunches up and it descends. So what the gal on the video said is we end up with kind of a high. I'll put an H for a high pressure there because it's descending. So we have high here and high there. And we kind of actually have a low here. I bet you kind of buy that because that air is ascending. We have kind of a low there. Cool. Let's see. So I think this next slide does this. So the air that descends, that's part of the Hadley cell. So basically you have air that hits the tropopause, goes north and south, it descends at 30 degrees north and south, and then once it splashes down here, it's got to go both ways. Some of it goes that way along the Earth's surface, and some of it goes this way along the Earth's surface. Now here's where you need to tie in what we talked about earlier about the Coriolis force. The Coriolis force causes a deflection to the right. So if you stand up here, at the Earth's surface and point down and go right, okay, do you guys buy this, that actually a surface wind, we create a surface wind here, that is what we call from the northeast. Surface wind of the Hadley cell to the northeast. Okay, that's actually called our NE, our northeast trade winds. I'll just put trades. Okay, right there. The other part of the Hadley cell, we'll just talk a little bit about the southern hemisphere. It comes this way, it goes 30 degrees south, it descends, and it's actually going to come a little bit, it's going to come along, not a little bit, but part of it's going to go this way, part of it's going to go this way along the Earth's surface. This that goes here, do you guys remember, deflection is to the left if you're in the southern hemisphere. So I'm going to put out my left hand, and so actually this along the surface is what those winds do. We call these the southeast trades, or trade winds. Okay, so along the surface, as part of the Hadley cell, we kind of have these, and actually we're going to talk about how they converge. It's Intertropical Convergence Zone. We kind of have these converging trade winds. Okay, but it's funny because this is where, if I was taking this course, I'd be like, wait, didn't we say, like, and actually Benjamin Franklin noted, because he had a cousin out west, didn't we say that basically we kind of have a westerly wind? And we do. but we're part of the feral cell, the Hadley cell. And also, didn't you hear, like, Christopher Columbus sailed he grabbed the trade winds to get over here from wherever Europe is. Over here, okay, here it is. He went like that, trade winds. Where's, okay, final answer, like that. Okay. So, all right, what else do we have up here? Oh, I think I got ahead of myself. So this descending air right here creates a high. One of the things we talked about earlier in this class, a lot of things come back to haunt us, right? We talked about a chunk of air cools as it rises. A chunk of air that's forced to come down warms. So actually we have this adiabatic warming right here at the edges of the Hadley cells. And oftentimes that's where our deserts are. Let's see what else. Horse latitudes, oh my gosh, that is a sad story for animal lovers. So here's the deal. If you are kind of here at the edge of the Hadley cell, the winds, if you're a sailor, the winds can be not very reliable. They're variable and light. So the horse latitudes got their name because if you were at point A and you need to get to point B, if you're sailing there, okay, and your winds die down, well then you look for things to lighten your load. I know, isn't that awful? Yep, I'm just saying. So horses, there's a lot of horse carcasses right out there. Isn't that terrible? It's true. That's why they're called the horse latitudes. Okay? All right. So, like I said, I kind of got ahead of myself. But that air that creates these horse latitudes, that air that creates this what we call semi-permanent high at the edge of the Hadley cell, part of the air will come along the Earth's surface going towards the equator. Part of the air actually will become part of the feral cell. That's going to be part of the feral cell. This part of the Hadley cell is what we call a surface northeast trade winds. That's what we call the prevailing wind. Prevailing wind just means what it usually is. Okay. So we have the northeasterly trades, which is part of the North Hadley cell. And we have the southeasterly trades, which is part of the South Hadley cell. Okay, so where they meet, actually the word doldrums, we can probably, if somebody says they're in the doldrums, that means they're kind of like, okay. So here, where they converge, sometimes that wind is kind of like the horse latitudes, kind of like, it's not very much. So the doldrums is right there, where the two trade winds meet. Okay, so that was the Hadley cell. Kind of got the Hadley cell. What's up with the feral cell? Well, to explain the feral cell, let's go ahead and look at that air that descended here. Okay, that descending air that kind of creates our deserts. Part of it goes and creates our northeasterly trades. Now, the part that splashes to the earth and heads towards the poles, let's look at that. So it splashes to the earth, it heads towards the poles, and it's deflected to the right. So deflected to the right, I got like that. Okay, so actually these create, and they kind of just are a pure, these are our westerlies. Sometimes they're called mid-latitude westerlies, or just the westerlies. Okay, mid-latitude westerlies. We could convince ourselves, if you wanted to, and deflection is to the left in the southern hemisphere, but actually the feral cell in the southern hemisphere is also a mid-latitude westerly. So now you already kind of have an idea when we talk about middle latitudes, what are we talking about? Well, we're kind of talking about there. Sometimes these are called middle latitudes, sometimes they're called subtropics. Okay, I guess the tropics would be here, the Hadley cell, tropics, tropic, subtropic, kind of. Okay, so those are surface winds. Good. Okay, so let's finish this feral cell idea, or talk a little more about this feral cell. So, about 60 degrees in both hemispheres, the air actually kind of scrunches together, or, did we get that right? the air goes up anyway. The air ascends. So think of air going up. And just like the air down here, it's going to hit the tropopause. It's not going to go beyond the tropopause. It's going to hit the tropopause, and it's going to go both ways. So part of it that goes this way is actually going to finish the ferrule cell, and part of it goes this way is going to be part of the polar cell. So that's kind of what we have. Okay. Cool. Then for the tippy top, the top or the cell that's closest to the poles. So again, we have kind of analogous cells in both hemispheres. I think it's best if we kind of think of, and I think the video did this, up here at 90 degrees, kind of think it's very cold, cold descending air. And sometimes I think of it like you crack an egg and drop it, okay, and it's going to go in all directions. Gooey, gooey egg. But you figure it's not going to, well, we'll talk more about this in a minute, but basically it's going to butt up against the, where's 60? 60's not very far. It's going to butt up against the ferrule cell. So when it butts up against the ferrule cell, it's going to rise, okay? So that's kind of, we have two rising things like that. All right, but when it comes down, I'll go ahead and do this slide so you guys can fill in the blanks here. Whoop. When it comes down, let's go ahead and do our little bit about deflecting to the right. So let's just say we go ahead and we crack our egg and we're going to let it drip down, but deflection is to the right. So deflection to the right, I got this. So notice at the surface, now these are surface winds I'm drawing right now on the board. Notice we have an easterly. We call this, do we call it the polar easterly? Yep. We call it the polar easterly. And you could convince yourself, wouldn't take too much convincing, I'm sure, but here in the southern hemisphere for our polar cell, we also have an easterly at the surface. Now, you're going to have to somewhere in your mind make sure you kind of connect what we talked about, and I think she even mentioned geostrophic winds. Remember, at upper elevations, we have that geostrophic wind, which is basically a westerly wind. So that's all kind of happening underneath that. There we go. Whew. What did we miss? Well, maybe it's coming up. So just to kind of add to what we've been talking about, this hot spot right here, and I put it at 0 degrees. I put it at the equator. It's not always at the equator. But the place where the two Hadley cells bump up to each other, that's actually called the ITCZ. And that stands for Intertropical Convergence Zone. And it kind of makes sense because intertropical means between the two tropics. Convergence, trade winds converging there. Intertropical Convergence Zone. And it is generally low pressure because air is rising. We have a kind of what we call a semi-permanent high here. Of course, this, and I'll go ahead and mark on here, that is about 30 degrees. So, of course, that must be the thing that's separating our Hadley. I'll put Hadley and ferrule. And this is polar cell. Okay, so we kind of have a subtropical high here where the air is descending. We have a subtropical low up here between the ferrule and the polar. And we have a polar high at the very top. So that's kind of what we have in a nutshell. But notice the title of this. In science, we do a lot of this, especially in introduction. It's idealized, which means it's not quite the real deal. This is more the real deal. This right here over the left. Okay, and if you kind of compare the two, you can see the hot spot, the Intertropical Convergence Zone. We're going to see some more pictures of the Intertropical Convergence Zone. You kind of see where we're going to see it kind of as it meanders. It kind of goes funky over land versus water. The other thing is we see not kind of a band for this highs, but we actually kind of see kind of little mini circles in our ocean basins. Maybe at break I've got this big old globe that's, well, not that big, but a globe that has the ocean currents on it. Okay, so we generally have these high pressures, semi-permanent highs in the oceans that are players. Do you see the little, this goes back to what we talked about in the previous unit. Do you see the direction? We called highs, do you remember we called them anticyclones? Almost sounds bad, but it's not. Highs are anticyclones. In the northern hemisphere, they should be going clockwise. So kind of keep that in mind. Cool. So that's more what it is than this. And that's even kind of idealized. Okay. All right. So one of my favorite phrases in this material is the wandering intertropical convergence zone. The wandering intertropical convergence zone. And we're going to see here kind of where that intertropical convergence zone is like 6 months apart. Not so surprising, just like the video said, not so surprising. When we're in June, okay, basically the northern hemisphere is hottest, you're going to see your whole intertropical convergence zone move that way. And the thing about it is when it moves, everything else moves, you know. So when it moves north, basically this Hadley, Ferrell, and polar need to squish together, okay? And these are kind of expanded, they got a little more room. Okay, so the intertropical convergence zone is going to move, and the whole cells move with them. A few slides ago, maybe 2 slides ago, this not less idealized version of the pressure systems, surface pressure systems, they had those H's over the ocean basins. That's what this slide is talking about. These semi-permanent high pressures. Okay. There are L's that kind of move too when the Hadley cell moves. And that we said that actually there are semi-permanent lows associated with this right here, which actually here in a minute I'm going to call that the polar front. The thing between the Ferrell and the polar cell is called the polar front. We can have semi-permanent lows there. Notice the title of this. It's talking about mesoscale winds, and I'm hoping you're kind of linking that back to something we talked about last week. Remember, there's 3 scales of winds. I started out today. There's the microscale, the mesoscale, which are local winds, kind of medium-scaled winds, and then there are the macroscale or global scale winds. So these are kind of middle-scale winds. And then, like I talked about, and you're going to see it here in some of our figures. Remember, in the northern hemisphere, we have anticyclonic movement, which is clockwise, okay, and anticyclonic movement around a high in the southern hemisphere is counterclockwise. So all that stuff to remember. So here's January. So you figure January, you would think that the southern hemisphere is kind of doing their thing. Getting the heat and all that. Okay, so find the intertropical convergence zone. It's that purple thing right there. So that's the hot spot. Notice how far it is from the equator. Well, where the ocean is, it's not too far, but where there's land, it's very far. It kind of dips down over land, and that's because land heats more quickly and cools more quickly. Make sure I didn't pocket dial somebody. Okay. Don't you hate it that when you do that? Oh, sorry. Okay. So you see your semi-permanent highs. Oh my goodness. Have you ever heard of the Bermuda Triangle? Okay, the Bermuda Triangle. Actually, it's kind of associated with that, with the semi-permanent high pressure. Somewhat seasonal, but they have some cool stories about the Bermuda Triangle. And hopefully you can get a sense for movement clockwise around the highs, and the lows, it's kind of hard to tell, but we can pick on this low up here, should be counterclockwise. Which I buy that. And these actually are isobars. These are back to isobars. So 1,002 millibars, 1,000, let's see, 6, so it'd be 1,005 millibars, 1,008 millibars, 1,011 millibars. Okay, So I actually have them side by side here in a minute, because like if I go back and forth, there's January, look close, and there's July. So we saw the purple line go up, okay, and everything moves with it. Yep. Here in a minute, probably after our break, we'll talk about actually these winds, these kind of winds that are associated with these pressure changes. These winds are going to drive our waters, or make our ocean currents. So I think that's pretty exciting. So here they are side by side. We have January and July, so you can kind of see the wandering intertropical convergence zone. I just think that is so poetic. Here it is, and here it is. I'll point out one thing we're going to talk about tonight are the monsoon seasons that they have in India. So actually, if we find India, you can already see that that intertropical convergence zone moves a lot. Okay, for 6 months apart. So that's what creates their monsoon seasons. They have a dry, hot summer and a cooler, wet winter. Okay. So I decided not to include it, but your textbook has a lot of neat things in it, including, actually they have just a little paragraph about some of the things that NASA are doing with tracking moisture in the atmosphere and where it dumps and where it doesn't dump. But you can just see, this is like a satellite image of the Earth, and where you see clouds, kind of that chronic bland of clouds, you figure we've talked about and this would be pretty moist because it's over oceans, got a lot of water here in the equator. As air rises, it expands and cools, and that warm or that moist air can go ahead and condense and give us clouds. And like we said, that actually is where the, go ahead and draw it on here. That's where our northeast and our southeast trade winds are converging. So I love that. That C in converging is the C in Intertropical Convergence Zone. I like it when things are named the way they should be named. So yeah, let's take a quick look at the monsoon seasons of India. Now, by definition, what a monsoon season is basically it has a dry, cold winter season and has a wet, warm summer season. So we're going to pick on India. Actually, I think I'm going to also introduce you then to a monsoon that occurs here in North America, in our southwest. So here's India. Well, before I show you, I'll show you. So this, you might recognize, actually is an excerpt of India in July. The Intertropical Convergence Zone is way up there over the Himalayas. Now, one of the things we know about mountains is they are a great source of lifting, and so actually that's what's going on, is we basically have wind ramming up against the mountains, lifting, and not only is it just, air, we have air ramming up against the mountains, not just any air, it's warm, moist air, okay? And so as it goes up, and it's carrying a lot of water vapor, as it goes up, it cools, it expands and cools and creates clouds and dumps. So they get dumped on, and you can actually see here them getting dumped on. So the reason it's a monsoon, that we call these monsoon seasons, a wet season, rainy season, and a dry season, is because it's caused by the movement in the intertropical convergence zone. So here we go. Here is the same neck of the woods. We have the intertropical convergence zone has moved significantly southward, which makes sense in January. So now what we have is basically, we have dry air, and we're going to talk about air masses in the next chapter. We have dry air ramming up against the Himalayas, and you're like, dude, they're going to rise and cool, but they don't have any moisture to give. Okay, so in this actually time, they're very dry where they were very wet 6 months earlier. So I also have this same topic in my chapter 8. So so I don't know, it's in there twice. So we have another monsoon that happens here in our southwest. And it's, to me, less obvious, okay? It doesn't specifically involve the Intertropical Convergence Zone, but if you read it, what it does involve is basically this mass right here. We know that land heats more quickly, okay? It's more stubborn to heat here. So basically we kind of have this warming, and one of the things we know about warm air is it's a relatively low pressure. So when it talks about low pressure, that's what it's saying. Nice and toasty, just a generally a low pressure. The other thing we know about low pressures then is you create a low pressure and you're going to have air moving in. So in this case, just because of its proximity to moisture, okay, basically we can get moist air moving in that wasn't there in the wintertime. So they can actually have seasonal flooding and stuff in the summertime that they didn't in the wintertime. So you can see the July, August, September, October, and that kind of that semi-permanent low that's created just because of the heating of land. Cool. Well, that's a perfect place to stop. I couldn't time that any better.